Hello everyone, welcome to my YouTube channel. In this design and analysis of algorithms tutorial, I will discuss how to find the longest common subsequence present in two given strings and the length of the longest common subsequence. First, I will discuss the subsequence concept and then I will discuss the longest common subsequence problem. After that, I will solve it in different way to approach the problem and determine the time complexity of that approach. So I will solve it with the brute force method and recursive method. Finally, I will show the memoization method, which significantly helps to reduce the time complexity of solving the longest common subsequence problem. So what is a subsequence? A subsequence is a sequence that can be derived from another sequence by 0 or more elements without changing the order of the remaining elements. Now let's understand it properly. For example, we have given a string AJK Its subsequence can be AKST and STT because they are following their order even if some characters in between are missing. But SAT cannot be subsequence because here we are finding out the matches. You should take care that if you draw a line between them, lines should not intersect with each other. So it means that S is appeared here. So A should be following that S, not at the backside of S. So it can take only those characters that are coming after S. So we see that maintaining order is important to be a subsequence. Now, if given two sequences are these, we see the longest common subsequence is ATBF. But if we select characters differently, we get a different subsequence, which is TABF. We see both LCS are 4 lengths long. So which one do we choose? The answer is that there can be multiple longest common subsequences, but their length will be unique or the same. And selecting any one of them is the correct approach. So now we have understood the subsequence and longest common subsequence concept. So let's comprehend a little bit of time complexity. So the time complexity is the computational complexity that describes the amount of time taken by an algorithm to run. So we need to determine the general form of time complexity of any algorithm mathematically. Now let's see some methods to solve this longest common subsequence problem and their time complexity. To solve longest common subsequence problem using the brute force method, let's take a string x with length m and another string y with length n. There can be a total of 2 to the power m subsequences of x when the length is m. For example, string x is ABC and string y is APQC. Here the length of the string is 3. So the total subsequences will be 2 to the power 3 or 8. So the subsequences are ABC, AB, BC, AC, ABC, and empty set. So if we compare all possible subsequences of string x with length y, string y, each subsequence will take big O n time to scan the whole string y. Here, the major flaw is the time complexity because to compare 2 to the power m subsequences of string x with n length long string y leads us to the exponential time complexity big O n into 2 to the power m, which is one of the worst case complexity we can get. So we should not solve the LCS problem in this approach. Well, let's look at the recursion solving method. This algorithm is for finding LCS with the recursive method. So here I have taken two strings that are terminated by /0. Here the parameter of this algorithm I and j will be worked as starting indices of strings and initially they will be 0, 0. If any of the characters is 0, then it returns 0. If the characters match, we add 1 and move on to the next characters in both A and B. If they don't match, we call a recursion and take the maximum length we can get by increasing A or increasing B. But this approach also has exponential time complexity, which is 2 to the power n. So we should not use it either. Let's see the simulation to understand it better. Initially, we compare A0, B0 and find out that they are not equal. So it will make two different recursion call where A will move to the next character and B will remain the same. And another one is B will move to the next character and A will remain the same. Out of these two calls, whichever gives maximum, it will take that result. For this left branch, we see that A1, B0 are not equal. So the same else condition will be applied again, resulting in two different branches, where in the first call, A will move to the next alphabet. So from 1, it will go to 2, and B will remain 0 only. And this in this side, one more call. So this is A1, but B will move on to the next alphabet. Here in two different branches, we can see that we have null character in A2, B0. So this branch will end and return 0. Now the other branch A1, B1 should be expanded because both characters are not the same. So it goes to the else condition and generates two different branches again, where on the left, A will move to the next alphabet and B remains at 1 only. So it will be A2, B1, which returns 0 as there is null character. And in the right side, A1, B2, where A remains same, but B will move to the next alphabet. So in B, it will go from 1 to 2. Here A1, B2 again generate two different recursion call since characters are not the same. So in the left side, A will be increased by 1 and B remains the same. So it will be A2, B2, which returns 0 for the null character. And from A1, B3, we get matched value. So it enters in the second condition, and in the second condition, it says that 1 plus the next call will be A will move to 2 and B will move to 4. And these both are null characters, so it returns 0. Now it will return back. So 1 plus 0 is 1. So the result of this is 1. 0 and 1, the maximum is 1, so the result is 1. Here also 0 and 1, so the maximum is 1, so the result is 1. Here is also 0 and here is 1, so the maximum is 1, so the result is 1. Now, if we solve the right branch A0, B1, they are matching. So it enters in the second condition, and in second condition, it says that 1 plus the next call. So A will move to 1 and B will move to 2. Now you see here, this is matching with this one. So now this part will continue here also. Now it will return back. So 1 plus 0. So the result of this is 1. And here this is 0. And here this is 1. So the result is 1. 1 plus 1 is 2. Here this is 1 and here this is 1. So the maximum is 2. So the result is here 2. So we have completed the whole recursion tree. Here in this complete recursion tree, we have a maximum value 2. So we have the longest common subsequence, that is 2 lengths long. The purpose of showing this simulation is that this recursion tree has calculated the sub-branch twice. So this is the overlapping problem. So if we solve this LCS problem with dynamic programming, we can store the previous values, and the stored values can be used when the same call occurs. This can be done with memoization, which reduces time complexity. Now let's see the condition of the memoization method. So if I or j is 0, then it returns 0. If the values in the subsequence matches, we take the value that is stored in the top diagonal and add 1 to it. And if the values don't match, we take the maximum value from the left and top of that index. Now let's see the simulation. Let's take two sequences A and B. Here we have taken a 2D matrix that has a column equal to the length of B and rows equal to the length of A. Let's set in the index 0, the length of both A and B are 0 according to the condition. That's how we completed the first row and first column with 0. Now in the index 1, 1, here A has a value B and B has a value A. So they are not equal. So we need to take the maximum value from the left and top of that index. So both have 0. So in them, so let's take the top one and place the value. Following this, we have moved on to the 1, 2 index and assign their values. Now, when we come to the 1, 3 index of the matrix, we get a match. So according to the condition, we need to take the value that is stored in the top diagonal and add 1 to it, and then assign that value in the 1, 3 index. And then we follow the conditions accordingly. In the last index of the matrix, we get value 2, which is the size of the longest common subsequence. If we look at the method, we can see that we have used the recursion method. But as values from the previous calculation remain, time complexity is hugely reduced. Calculating the time complexity, we get m into n, which is way better than exponential time complexity. To find out the longest common subsequence, we have to follow arrows diagonally, which we can notice in this matrix. Tracing back, we get BD, which is our longest common subsequence. Thank you, everyone.